You know, when you see a perfectly shiny chrome bumper, or you think about pure metals like sodium, where does that stuff actually come from? It's not like you just dig it up out of the ground looking like that. The secret is an amazing process that basically runs chemistry in reverse, using a blast of electricity to make things happen that would never happen on their own. Okay, let's jump right into the incredible world of electrolysis.
So we all get how a battery works, right? That's a galvanic cell. It takes a chemical reaction that wants to happen, and it turns that energy into electricity. Well, electrolysis, which uses an electrolytic cell, is the exact opposite. It's like running the movie backward. You take electricity and you use that energy to force a chemical reaction to happen. Think of it like recharging a battery. You're using power to reverse the natural flow.
All right, so let's really get into the nitty-gritty here. We're about to see how just applying a voltage can make the chemically impossible totally possible, which opens up this whole universe of industrial manufacturing and cool material science. So what is electrolysis officially? Well, it's a process where we use electrical energy to drive a non-spontaneous chemical reaction. The key word there is non-spontaneous. These are reactions that nature will not do for free. We have to supply the energy. And this isn't just some neat lab trick. It's the absolute backbone of huge industries, everything from creating chemicals and refining metals to putting the chrome finish on a car part.
To really see this in action, let's look at a really dramatic example. Table salt, sodium chloride. This stuff is about as stable as it gets. But if you hit it with enough electricity, you can literally tear it apart into its original elements: superreactive sodium metal and poisonous chlorine gas.
So how do they do it? Industries use something called a down cell. First, you have to melt the salt, and we're talking crazy high temperatures. You do that because you've got to get those sodium and chloride ions free and moving around. Then you stick in two electrodes, a positive one called the anode and a negative one called the cathode, and you crank up the voltage.
Okay, so the power's on. What happens? At the positive anode, all those negatively charged chloride ions are drawn to it, but when they get there, bam, the voltage is so strong it just rips their electrons right off. That process, losing electrons, is called oxidation, and it forces those chloride ions to pair up and bubble off as chlorine gas.
Meanwhile, over at the negative cathode, the exact opposite is happening. The positive sodium ions are attracted over there, and the external circuit is just waiting to pump them full of electrons. This is called reduction, the gain of electrons. The sodium ions are basically force-fed electrons, which turns them back into pure, liquid sodium metal.
And just like that, think about what we just did. We took one of the most stable compounds you can think of, and just by pumping in electrical energy, we split it into two extremely useful and extremely reactive industrial chemicals. That is the power of electrolysis. Okay, that was in a giant vat of melted salt. Pretty straightforward. But what if we just dissolve the salt in water? Well, now things get really interesting. Because now the electricity has a choice. It can react with the salt ions, or it can react with the water itself. It becomes a chemical showdown.
Let's check out the anode first, the positive one. We have two contenders ready to be oxidized, the chloride ion from the salt and the water molecules themselves. Now, we can look at these numbers, the standard potentials, to see who's more likely to react. The rule is the lower, less positive number wins. So just looking at the data, you'd put your money on water, right? It looks like it should be easier to turn water into oxygen.
Now, let's head over to the cathode. Here, the competition for reduction is between water and the sodium ion. Again, we look at the numbers, and wow, this one isn't even a fair fight. It is way easier to reduce water to form hydrogen gas than it is to reduce a sodium ion. Water wins this one by a total landslide.
So what's the final result? Well, just as we predicted, water wins at the cathode and we get hydrogen gas. But at the anode, surprise, chloride gets oxidized into chlorine gas. You're probably thinking, wait a minute, you just said water should have won. And you're right, it's because of a real-world quirk called overpotential. But the big takeaway here is that this whole setup is the basis for a massive industrial reaction called the chlor-alkali process. It's how we use salt water and electricity to make three vital chemicals: hydrogen gas, chlorine gas, and sodium hydroxide.
All right, let's shift gears from making industrial chemicals to making things beautiful. Let's talk about electroplating. This is how we use that same principle of electrolysis to put a super thin, perfect layer of metal onto pretty much anything.
So, why bother doing this?
Oh, for tons of reasons. To stop things from rusting, to make a surface harder, or, just to make something look nice and shiny, like silver-plated forks or gold-plated jewelry. It's done with all sorts of metals: copper, chromium, nickel, you name it.
So let's picture it. Say we want to plate a plain old steel spoon with a beautiful layer of silver. Here's our setup. The anode, our positive electrode, is just a solid bar of pure silver. The spoon itself? That's our cathode, the negative electrode. And we dunk them both into a special solution that's full of dissolved silver ions.
When we flip the switch, the silver anode starts to get oxidized. That means atoms of solid silver have an electron stripped away, and they dissolve into the solution as positively charged silver ions. The anode is literally sacrificing itself, slowly dissolving to provide the silver for the plating.
And now for the magic part. The spoon is our negative cathode. All those positive silver ions we just made are immediately attracted to it. When they reach the surface of the spoon, the circuit is right there, ready to give them their electron back.
And this right here is the key reaction. The silver ions get reduced, they get that electron back and turned back into solid silver metal. But now they're not on the silver bar anymore. They're stuck in a perfectly thin, uniform layer right on the surface of our spoon. And that, in a nutshell, is electroplating. Now, this whole process isn't just some kind of random art project. It's incredibly precise. We can actually use the laws of electricity and chemistry to calculate exactly how much metal will be deposited and exactly how long it's going to take. And the key that connects it all is this one magic number, Faraday's constant. This is the bridge between the world of electricity, current and charge, and the world of chemistry, atoms and moles. It tells us the exact electrical charge carried by 1 mole of electrons. This number is the fundamental conversion factor for pretty much any electrolysis calculation. Let's put this to the test with a real-world problem. Imagine you need to plate a very specific, very thin layer of chromium onto a car part. You know the part size, you know the thickness you need, and you know the electrical current you're using. The million-dollar question is, how long do you run the process?
Well, we can break it down into 4 simple steps. First, you calculate how many moles of chromium you actually need to get the right thickness. Second, you look at the chemistry. Each chromium ion needs 3 electrons, so you can figure out the total moles of electrons required. Third, you use our magic number, Faraday's constant, to convert those moles of electrons into the total electrical charge you need in coulombs. And finally, since current is just charge over time, you can do some simple math to solve for time.
And there's our answer, 11.0 hours on the dot. This is what makes electrolysis a tool of precision engineering. Manufacturers can control the current and the time to get the exact result they need, every single time, with no guesswork. So from creating the basic building blocks for our modern world to crafting the beautiful finishes on everyday objects, electrolysis is this incredibly powerful tool that lets us command chemistry with electricity. It forces matter to do what we want, creating materials that just wouldn't exist otherwise. It really makes you wonder, as our technology gets even more advanced, what other new possibilities is this amazing process going to unlock for us in the future?